Now we have talked about mechanisms which cause recombination inside the bulk, but another evil which occurs at the surface, and we have talked about it before, is these surface recombination, and it happens due to these defect states present at the surface, right? And it depends, it's usually characterized by this parameter called the surface recombination velocity. And you already had some experience playing with that in your problem set 2 when you're inputting that surface recombination velocity in your calculation. So if you have, usually if you have no zero surface recombination velocity, then your carrier profile, it remains flat. If you have a very high surface recombination velocity, then your carrier profile, it essentially falls off as you reach the surface, right? So this is again, this is captured in this term surface recombination velocity, but another dilemma is to how to measure it. So the way this is usually measured is that you take a wafer which has a very high bulk lifetime, and then you have an unpassivated surface, or you have high recombination at the surface, and then you measure its effective lifetime. And assuming it has no recombination in the bulk, you assume that all of this recombination must have been happening at the surface. And you have two surfaces, one at the front and one at the back. So this factor of 2 comes in. And you use that to essentially estimate your surface recombination velocity. So you use that same setup, but now you use a piece of semiconductor which has very high bulk lifetime. And then you use that to measure your surface recombination velocity. Usually in this formulation I've assumed that the bulk lifetime is negligible, but usually that plays a role as well. So you use this more complicated equation where you assume that the bulk lifetime is there as well, and then this surface recombination velocity is there as well, and again you measure the effective lifetime and back calculate your surface recombination velocity. So I want to give you some feel of what these surface recombination velocity numbers look like. So if you have a very unpassivated surface, if you have like a bare silicon surface, you can get very high surface recombination velocity. So this surface recombination velocity, it's it could be as high as 10 to the power 5 centimeter per second. That means it will deplete a very large part of your cell, and even up to like few hundred nanometers away from the surface, all the carriers which are generated would essentially just recombine at the surface. So the techniques that are used is to essentially passivate this using silicon oxide, and then again you do further anneal. You do anneals in forming gas so that you passivate the remaining of the bonds with atoms such as hydrogen. So you want to passivate as many of your bonds at the surface. And the best numbers which are typically obtained with with the thermally grown silicon oxide plus this hydrogen passivation, you can get surface recombination velocity. You can lower it all the way up to 1 to 10 centimeter per second. But on most common surfaces, the values you get are between 10 to 100. Most of the commercial cells you get something between 100 to 100. And whenever you have metal contacted surface, that again gives you higher recombination velocity. So many times you want to limit the amount of metal which is touching your cells. So even at the back, people use these point contacts because they want to minimize the amount of area which is touching the metal, because a surface which is touching the metal has higher recombination velocity. Again, things that we talked about for maximizing light trapping, such as texturing the surface. So those are again not very bearer of good news for surface recombination velocity. So whenever you texture the surface, you create these defects or dislocation at the surface. And the other thing you do is you increase your surface area. And those things essentially all maximize your surface recombination. So it's especially difficult to reduce your surface recombination if you have a textured surface. So things which maximize light trapping, but they're not as good as for minimizing your surface recombination. Okay. So then the next thing is, how important is the surface recombination velocity? So you already got some feel of it when you did that problem with PC1D in your problem set 2, and you inputted that high surface recombination velocity into your device. But that was for a dimension, for a cell which was intermediate in thickness. So you see that for a cell which is, let's say, 100 micron, my efficiency, if I increase my surface recombination velocity from 10 to 1000 to 100,000, it falls from, say, 20 to 15%. Okay. But if you would go back to that same simulation you did and just change the thickness of your cell from from hundreds of microns to just make it much thinner. Okay, so if you make it much thinner, you'll see a much drastic effect. So you'll see your efficiency, it drops all the way, from 17 to very quickly it becomes even below 0, or it becomes below 10. It's not even in this curve, but it would become very small if you have a very high surface recombination velocity. A good way to understand is that if you have a thinner cell, right, the surface to volume ratio of that cell is much higher. It has much larger surface as compared to the volume, right? So whenever you have a thinner cell versus if you have a thick cell versus if you have a thin cell, your surface plays an even important role. So it's passivating this surface and reducing this surface recombination velocity. It's even a bigger challenge for all of these thin film technologies. So all of these people who are like the companies which we heard from, say, Select Cell or Alta devices, which are trying to make these thin cells, for them to passivate the surface is very important. And when we'll talk about these thin film cells, again, this passivating the surface, it becomes even more important issue. Okay. So then, what are some of the ways I can minimize this surface recombination? So I can, the most common thing is to passivate the surface, passivate the dangling bonds on the surface, and passivate them using a good quality of silicon oxide, and then I can use this hydrogen passivation in conjunction with that. And then I want to minimize the defects I create while texturing, like while polishing or while this chemical etch process which is used for creating this texture. And then again, you want to minimize contamination. And the other way to reduce this surface recombination velocity, again something you already know, is to use surface field, because this surface recombination is maximum if you have both kind of carriers available. So if you have both your electrons and holes available at the surface, so if your surface has both electron and hole, the surface recombination would be even higher. So what you do is typically you create a surface field in the back using a back surface, which essentially repels one kind of carrier. So over here it let's say repels the electrons away from the surface, and that helps in minimizing this surface recombination as well. And the other way, which is now being a lot of people are trying to commercialize, is using these dielectric films which have fixed charge. Let's say a lot of positive fixed charge. So this positive fixed charge will repel the holes away from the surface. Similarly, if you have negative fixed charge, it will repel the electrons away from the surface. So there's a lot of research which is going on how to develop these films such as aluminum oxide, which have a very high amount of fixed charge, which can create this repel one kind of carriers and helps you minimize this surface recombination. But minimizing the surface recombination is again very important. Okay, so now you know all kind of bad things which can go in your cell. You could have Shockley-Reed-Hall recombination due to traps. You could have Auger recombination, especially if you're operating at high concentration. You can have the surface recombination. So most of these things, this has been analyzed that what would happen if you have no recombination. So let's say a hypothetical situation where you have no radiative and no surface, no Shockley-Reed-Hall recombination. So if you have no radiative recombination, essentially this term will become 0, right? Your this term which comes around due to recombination in the depletion region, or due to this radiative recombination, it will become 0. And people have analyzed it, that what is the maximum VOC, or what is the maximum maximum efficiencies you can get in that case. And for the case of silicon, you can get up to very close to 30%, around 29%, if you get rid of all the recombination mechanism. And most of that increase when you improve your, when you reduce your recombination, it comes in this VOC. So whenever you reduce your recombination, you lower this J01 term, right? So you lower this term over here, and your VOC essentially is given by this formula. So if you lower your recombination current, your VOC increases, and it has this log dependence. So for every like decade of improvement in your off current, you see a linear increase in your open circuit voltage. So whenever you reduce your recombination mechanism, you see that your open circuit voltage shoots up. Okay. So most of these, if you try to reduce these recombination mechanisms both at the surface and the bulk, you'll see most of the gain coming in the form of your open circuit voltage increase. Okay.